All right, hello Polistat. I'm going to be explaining the second method that we came up with for implementing the state correlations in our simulations, which we dubbed adding after the fact. So in this video, what I'm going to be doing is explaining the methodology behind that method in a more artistic manner. So as pasted over here, we have that blurb from the forum, and I'm going to be going through it and trying to explain each sentence. So the first sentence we have is we choose a random number from each state's normal distributions. So each state's normal distribution, which I'm sure Carlos has touched upon, but to be redundant, is after we combine together the BPI, combine together the poles, and then the demographics, we're going to get some mean and get some degree of variance. And to take, for example, in this video, let's use the great state of Michigan. So what that might look like is we get standard deviation based on that mean what that might look like, we get some normal distribution based on that mean and standard deviation, which might look like this. And we can say it's centered at 0.42. That's the mean, which means on average, 42% of all of Michigan votes for Trump. And for this normal distribution, let's say it has a standard deviation of 0.04. So that means one standard deviation away would be 0.46. And one standard deviation below would be 0.38. And then what we're going to do is we choose a random number based on this standard deviation, based on this normal distribution. And that means that for all the random numbers that we take, the frequency of which numbers appear is based on this normal distribution. So let's say we run this simulation one time, and this time we got some random number. X equals 0.46, right? So this time we ran the simulation, we took a random number from that Michigan's normal distribution, and we got 0.46. Now what we're going to do is find the difference between that state's random number and that state's mean. So that means it's going to be X minus the mean, which in this case is going to be 0.46 minus 0.42, which is in this case positive 0.04. There. So we do the same thing for all the other states and DC. We create a normal distribution based on each state's standard deviations and their means, and then we take some random number from that normal distribution for each state, and then calculate that difference between the mean and that random number for each state. So by the end of that first sentence, we have 51 differences, right? And now I'm going to condense that into some words, which I've already written out. Just down here. There. So this is what we just saw. We see for Michigan, it is a normal distribution centered at 0.42 with a standard deviation of 0.04. Then, for example, I had two other states, Wisconsin and Florida, which have their respective normal distributions centered at their means with their standard deviations. And then written under here are those correlations between each of the states. So from a correlation matrix, we can see how correlated one state is with every single other state. And I've just written out the ones that we care about for this particular example. And now, as we just said, when we ran the simulation once, we got that for Michigan, we had a simulated value, of 0.46, right? And that gave us a difference of 0.04. We do the same thing for Wisconsin. We say we ran the simulation. We got a simulated value of, let's go with 0.40. And that gives us a difference of negative 0.03. Same thing for Florida. We say its simulated value is, let's go with 0.51, giving us a difference of 0.01. And we do the same thing, find their simulated values and differences for all the other states. And now the most confusing part is then to calculate the overall result, we would add the weighted average of each other state's differences to that state's random number. And to explain that, this total, this overall result would be, for Michigan at least, would be its simulated value, which is 0.46, plus the weighted average of every other state's differences. Now what that looks like is, let's take Wisconsin's difference, which is negative 0.03, and multiply by Michigan's correlation to Wisconsin. And in this case, that is 0.7. Then I add Florida's difference, which is 0.01, and multiply by Michigan's correlation to Florida, which in this case is 0.2. Then do the same thing for all the other states, adding their differences multiplied by their state's correlation to Michigan. Then I'm going to divide that all by the total of all the correlations to Michigan to get our weighted average. So this is our overall result, that state simulated value plus the weighted average of every other state's effects. Now to find the total overall result for Wisconsin, I do the same thing. I take its simulated result, 0.40, and then add the weighted average, which is going to be Michigan's difference, which is 0.04, multiplied by Wisconsin's correlation to Michigan, which is this case 0.7. Then add Florida's difference, which is 0.01, multiplied by Wisconsin's correlation with Florida, which is 0.3. Then I do the same thing for all other states, adding together their differences multiplied by that state's correlation to Wisconsin, and then divide by the sum of all the correlations to Wisconsin to get our weighted average. So therefore, our total is that simulated result for Wisconsin plus the effects, the weighted average from all the other states. And the same thing applies for Florida, which is going to be 0.51 plus yada, 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 that weighted average, right? So this total is calculated for all other 51 states, and that's going to be, yeah, that's the final result for that state. And then whether or not, if that's below 50 or above 50, that's going to be a Trump win or a Biden win. The difference between this method and the first method is that this method isn't choosing one state to be like the center of that one simulation, because we're taking random numbers from all 50 states plus DC and combining them together. So in a sense, every single one of these overall results are the combination of 51 different random numbers. So compared to the first model, this would be much less volatile because there aren't as many negatives, there aren't many cancellations going on. In a sense, that also means it's more realistic because all the states have some impact on each other, whether it is little or small, and this is a model that's trying to account for all of those tiny effects. So whatever one you think is better, if you want more realistic with more like effects, or you want to see a more volatile model that might get you more extreme results, that's up to you guys. Hope this video was some help, and signing off.